Okay, so here we go. This is 1.5. So there's a few different things in here. The main thing we're going to talk about today is inverses of functions. But there's a couple other little details that they throw in as well. So we'll start with this whole parametric defined functions. So this is something that we'll dive a lot more deeply into when we get into semester 2, but I just want to give it a quick introduction now. These are pretty basic and pretty straightforward. So the idea is you guys are used to functions that look like this, where if I give you an x value, you know you can plug it in and find your y value. That's what you guys have seen since Algebra 1. So a parametric defined functions will give you both x and y values in terms of t. So instead of building a table with x in the left-hand column and y in the right-hand column, we're actually going to build a 3-column table. We'll pick our t values. We're actually going to have 2 different equations, one for x and one for y. And we will fill out those columns the same way that we would have before. We're just plugging this t value into 2 different equations instead of 1 equation. So that's really the only difference. And they use t because typically in applications of this, t represents time. So the x and y would be the position of something over time. Any of you take physics already or in physics right now? So with like projectile motion, there's an x equation and a y equation, and they're both in terms of t. If you haven't gotten there yet, you'll recognize this when you get there. Anyways, so let's do an example. So you're going to see some problems in your assignment where it's just like this. They give you these 2 equations, and they're going to say, for a value of t equals something, we're going to do -3, find me x and y coordinates. So very simple. All we have to do is take our x equation and plug -3 in place of t. So I'm rewriting my x equation. And I'm putting -3 where the t used to be. And then evaluate that. -3 squared, that'd be 9 plus 1, we got 10. That's what I'm coming up with for my x value. So my x coordinate will be 10. Go ahead and put that on my table down here too. And then take that same t value, -3, let's put it in for the y equation this time. So -3 plus 1 gets us -2. And there we go. So 10 comma -2 would be my ordered pair when time, or t, is -3. What do you think? Not too bad? Go ahead and fill out the x and the y columns here. You don't really need to show work for these if you're able to do stuff in your head. And then let's plot those points. So -2 squared is 4 plus 1 is 5. Yeah, 1 squared is 1. Plus 2 is 1. 2. 4 plus 1 is 5. 9 plus 1 is 10. Plus 1, -2 plus 1. -1 plus 1. 4. Have you guys seen these types of functions before? Where you have an x equation and a y equation? Oh, okay. It's a lot like what you spent a lot of time first semester in Algebra 1 doing, right? Building a table, plotting points. We just have 2 columns of the table to fill out this time around. the neat thing about these graphs, when we use a parametric defined function or relation to draw a graph, is that the graph is not just a shape, it represents the path of some object. And when we get into this, and I believe it's in chapter 6, we're going to be looking at some actual objects that are flying through the air, or it could be the path of a boat or an airplane or something like that. We don't need to worry about that too much right now, but this shape, it's kind of a sideways parabola, is actually representing like the motion of something. And there's a direction to this that's implied with it as well. As t increases, whatever this object is going to travel in this direction around that curve. But for right now, if we can build the table, draw the graph, we're happy. You guys feeling pretty good about that? Okay. This next part is the one it's not tricky, but for some reason, this is always one of the lowest scoring items on our first test. I don't know if it's just because we barely spend any time on it, or if it's one of those things that's just so simple that we forget about it. I'd urge you to put a star next to this and make yourself a note, review before test. Finding a relationship between x and y by eliminating the parameter. So the idea here is sometimes we have a physical situation where it's easy for us to write an equation for x and y separately. But there are some times when we don't want to have sort of three variables to deal with. Sometimes we want to eliminate the parameter t so that we've got a single equation that's just x's and y's in it. Okay, and the process for doing this is pretty straightforward. It's just substitution. What we're going to do is we're going to pick one of these equations, and it doesn't matter which. We'll pick one of these equations. We'll get t by itself. So we'll end up with an equation that says t equals something. And we'll take whatever that something is, we'll put it into the other equation in place of t. And then we'll just have an equation with all x's and y's. It's kind of like when we're solving a system of equations by substitution, how we get rid of the x's or get rid of the y's by substituting something in place of the x or the y. So if you had your choice with this system or this set of parametric defined equations, would you choose to get rid of t in the x equation or the y equation? There's no wrong answer here, but which one would be simpler? I think the y equation looks simpler to get x by itself. We could just subtract 1 from both sides. Here it looks like we'd have to do a square root on both sides. We might have to do like a plus or minus dealy. This is not going to require that. So let's do that. So I'm going to copy my y equation down here. So y equals, and I didn't leave you a whole lot of room here. I apologize for that. Y equals t plus 1. And I'm just going to do a little bit of work here to get the t by itself. So we'll do minus 1 on both sides. And we'll get y minus 1 equals t. So the first step is always pick one of your equations, get t by itself. And then bring that into your other equation. My other equation was x equals t squared plus 1. I am going to substitute in place of my t that expression that we just found. So this y minus 1 that we just found here is going to pop right into that equation in place of my t, because it's equal to t, right? And we would get that. Now we have an equation that just has x's and y's and there's no t's. If we were to graph this equation, I don't think you guys didn't spend any time graphing sideways parabolas, did you? So that's okay. That's okay. If you were to graph this equation, you would get this sideways parabola right here. All right, so that would be it. This would be my final answer. Now, question always comes up, is that simplified? Should we do anything to that? And I would say that's kind of a judgment call. Like, I kind of like the way this is because this looks like vertex form to me. You guys remember vertex form for a parabola? So I probably wouldn't multiply this out because I like this. I can look at this and see that my vertex is going to have a y coordinate at +1 and an x coordinate at +1 also. And that would help me find my vertex and its opening to the right. If, however, on a test, if you were to multiply this out and do combine like terms, that would be fine too. If I had instructions that said, simplify so that your final answer contains no parentheses, then I would expect you to be able to multiply this out. Okay. So I'll be specific, but if you're ever unsure on a test, like, does he want me to go further with this? You're always allowed to ask. Put your hand up or bring it up to me and say, do you need me to go further than this? What if I had asked you to multiply this out? Do you guys feel comfortable doing that? Why don't we practice that? Go ahead and multiply that out and get me a different version of this answer. If I had included the instructions to simplify so that there are no parentheses in your final answer, what would your final answer be? I'm checking to make sure that we have mastered this shortcut of squaring a binomial. Did your final answer have this -2y in it? If it did not, then you're making a super, super common mistake. When we're squaring a binomial, we can't just square the first thing and the last thing. You're leaving out the oi in the FOIL. So if going from here to here is you're not understanding what I did there, get my attention sometime and let me teach you a shortcut that's going to save you like whole minutes of time later on in this year. We'll be squaring lots of binomials. Any questions here? Why don't you guys give it a shot? Why don't you guys give it a shot down here, see what you can do. Do the whole shebang. Give me some XY coordinates, graph them, and then do the whole eliminate the parameter thing. There are 2 versions of this final answer that would be equally awesome. I'll let you guys work through that. Let me know if you have any questions, but I'd be happy to go back and show my process if anybody's, yeah. Which part? Like these, like the graph? I'm just plugging these numbers into this equation. So -3 plus 2 is -1. And -2, if I plug it in for t here, -2 plus 2 is 0. Okay. And then, and these are, like, you're going to find some patterns in these. Hopefully, you know this is a linear equation. So, and it's going up by 1 each time. So you should be able to kind of, once you see that pattern develop, fill those out. This is y equals 3t, so 3 times -3 is -9. -2 times t is -6. -1 times, I'm sorry, -3 times 3 is -9. -2 times 3 is -6. -1 times 3 is -3. And then once you see the pattern there, then that goes a lot faster. And then these 2 answers, you would have probably only gotten one of these depending on whether you chose to get the x equation, to isolate t in the x equation or isolate t in the y equation. I think most of you probably isolated t in the x equation on this because you'd rather subtract something from both sides than create fractions. Smart move. Me too. So if you did that, you would have ended up with x minus 2 equals t, and then that x minus 2 goes into this equation in place of the t, and that's how we get to there. So you'd get y equals 3 times x minus 2. And then I distributed because to me it made more sense to have it in this format because this y equals mx plus b, and it's easy to kind of see what's going on in the graph. You could leave it like this. This is kind of like point slope format. All right, other questions? We're moving on then. All right, let's get into inverses. So the rest of the lesson's all about inverses. And I know you guys talked about inverses last year. Do you remember the big thing about inverses? What do inverses do? So I got a machine, I got a function, and this machine it makes cheeseburgers. Cow goes in, cheeseburger comes out. Okay? Cow in, cheeseburger out. What's the inverse of this function? What would it do? Cheeseburger will go in, cow comes out. It just undoes whatever the function was. Okay? So inverse, the big idea is that inputs and outputs swap. When we're talking x's and y's are our inputs and outputs. So what I hope you remember about inverses is that anything having to do with x, when you find an inverse, is going to kind of switch over to the thing having to do with y. So this has to do with like coordinates. So if the point 0.5 comma 2 is on my function, then 2 comma 5 is going to be on my inverse. It also has to do with domain and range, because domain and range have to do with x and y. So if I know my domain for the function, that's going to become my range for my inverse, and vice versa. You guys remembering kind of the big idea is you're swapping inputs and outputs, or x's and y's. So there's a couple ways we can find inverses. We'll talk about it graphically first, and then we'll get into the algebraic way, which is kind of where we'll focus our attention. So first things first, I'm going to do this a little bit out of order. Let's do domain and range for this original function. Can you guys practice finding domain and range? We're finding them graphically here. We don't have an equation for this thing. So find the domain. We're just looking at the graph, and we associate domain with x. So if you look at that graph and ask yourself what x values appear on the graph, I'm hopeful that you're seeing that 0 appears on the graph and anything bigger than 0 appears on the graph, right? So I'm hopeful that you're able to look at that graph and come up with this domain, 0 to infinity, including 0. And then range, same idea, except you're looking at the y values. So look at the y values. Remember, we always go from bottom to top when we're talking about range. So look at what's the lowest. Does it go down to negative infinity? This one does not. The lowest y value looks like 1. And 1 is included, so I'll use brackets. And then this arrow is indicating that it's also going to go up to infinity. So there's our original function. The domain is 0 to infinity, and the range is 1 to infinity. Any questions about that? We haven't done a lot of that in this class. This is one of those things I assume you're comfortable. Is that a good assumption? Is it good with that? All right, so can you already predict without knowing what the inverse looks like, what its domain and range are going to be? I'm hopeful that you can. Go ahead and write down what you think it is. We're going to find, right now, without even knowing what the inverse is or what it looks like, we're going to find the domain and range, because we know that anything involving x and y, when we do an inverse, they're just going to switch. So the inverse's domain should be the same as the range of the original, 1 to infinity. And the inverse's range should become the domain of the original, 0 to infinity. We'll go ahead and graph the inverse function now, and we'll check and see if that works. All right, so there's a way we can do this with reflections that you may or may not have learned in geometry. For me, the easiest way to graph an inverse, if I've got a graph already, is to just make note of what your original coordinates are and then flip them. Like this point here has coordinates 0, 1. So if 0, 1 is on the graph of my function, then flip them around. 1, 0 should be on the graph of my inverse. This point right here has the coordinates 1, 2. If 1, 2 is on the graph of my function, then flip them around. 2, 1 should be on the graph of my inverse. So this looks like 4 comma 3, so we'll go 3 comma 4. Comma 4 is going to give me 4 comma 9. How do we do on our prediction about domain and range for the inverse? Does that match what you're seeing on the graph? No. The domain is starting at 1 and going off to the right, includes all the positive numbers after 1. And the range is starting at 0 and going up. Totally works. All right. You may have learned in geometry that we can also accomplish this by doing a reflection over the line. Does anybody remember the special line that we reflect over? Could you sketch it on here? Could you sketch what the line of reflection would be? This is a symmetrical shape that these two things make. What is it? Yeah, that diagonal line, right? Yeah, totally. This line right here. It has an official name. The official name is just its equation. Y equals x. Y equals x. In geometry, you learn that any point that's on the line of reflection won't move when you reflect it. This point right here would not move because, well, it's x and y coordinates are exactly the same. So if it's on y equals x, then it means its x and y coordinates are the same. Just some connections back to geometry. All right. So do you feel confident that if they provided you a graph, you'd be able to sketch an inverse, find domain and range? Excellent. Okay. Have y'all ever learned about the horizontal line test before? Vertical line test, that's way back to Algebra 1. Have you learned about the horizontal line test before? Oh, this is going to be new. Awesome. All right, well, let's review. The vertical line test tells us what? Tells us if, someone just said it. Can you say it louder? If it's a function. So if I look at a graph and I do a vertical line test and it passes, that means that graph is a function. If it fails, that means it's not a function. There's also a horizontal line test. Anybody want to guess what that tells us? It has something to do with the inverse. And also this thing here, this word here is in it also. So it tells us if the inverse is a function. We're going to be dealing in the second semester with some trigonometric functions, and we're going to be interested in knowing whether the inverse of a particular function is also a function. You'll see why later on. This is a quick way that we could test. So like, for example, if I looked at this graph right here, this is a sideways parabola. Is it a function? Does it pass the vertical line test? No, it does not. Without actually finding the inverse of that function, though, could you predict whether this thing has, or this thing's inverse is a function? Would it pass a horizontal line test? Same rule as a vertical line test. It would pass a vertical or a horizontal line test. That tells us that the inverse of that thing is a function. Anybody know what this second one is a graph of? It's a sine graph. Yeah, this is like sine of x would be the parent function for it. Could actually be cosine also. And sine and cosine are functions, yes or no? Do they pass a vertical line test? Yep. Is the inverse of sine and or cosine a function? Would they pass a horizontal line test? No, that would fail miserably, wouldn't it? Like in an infinite number of places, because that pattern goes on infinitely. So that's a no. And that actually becomes a problem for us because you guys have actually used inverse sine and inverse cosine before. Think back to trig in geometry. Remember when you were solving for an angle, you used the inverse sine button on your calculator. You had to do like second sine or second cosine to get it. So how were you able to use inverse sine and inverse cosine when we've just shown that sine and cosine don't have an inverse function? Dun, dun, dun. We'll deal with that. Sorry, you're going to have to wait until like, I don't know, May for us to get to that. Keep you on the edge of your seats. Stay tuned. Turns out we have to do some fancy footwork with our functions. We'll get to it. Don't worry. How about this last one? Is it a function? Yes. Is its inverse a function? Yes. These are special functions. These ones that are functions and also have inverses that are functions. They're super useful to us. They're useful to us because anything you can do to a number with that function, you can also undo it. Think of an inverse as kind of doing something backwards. They're so special that they get a special name. They're called one-to-one functions. They've got interesting properties in algebraically, and then you'll learn some cool stuff with them with calculus as well next year. All right, now we're ready to get into the nitty-gritty. You guys ready to do some algebra? Woo! This is the best part. Finding inverses. So, 1.2, the main thing that we did in 1.2 is I gave you functions and you found the domain algebraically, right? Remember how I have not asked you to find the range of anything algebraically yet? Well, after today, I can ask you to find the range algebraically. And how are you going to do it? Well, you're going to find the inverse algebraically, which I'm about to show you how to do, and this will be review. I know you guys have seen this before. And once we have the inverse, how am I going to find the range of the original? We find the domain of the inverse. The domain of the inverse is going to end up being the same as the range of the original. So after I show you this, you will be capable of finding both domain and range of a function algebraically. Range takes a little bit of work because you got to find the inverse first. So let's go ahead and do it. Actually, let's do this. Before we get started finding the inverse, let's talk about the domain of the original. Look at this function. It's 2x plus 10. What is the domain of the function 2x plus 10? It's everything. There's no radicals. There's no fractions. Those are the only things that we're looking for at this point. So I agree with you. The domain's everything. Negative infinity to infinity. We can fill out that part of this table down here. Actually, we should be able to fill out something else in this table down here. We should be able to use that to figure out what the range of our inverse is. Now, we don't even know what our inverse is yet, but we know that its range should come out to be negative infinity to infinity. All right, let's do it. I don't know why I put these here. I'm going to just cross these off. We don't need to. I don't really do much for us. All right, so here's my function. I'm going to rewrite it as y equals 2x plus 10. Our first move is always going to be to swap x's and y's. So all of the x's become y's and all of the y's become x's. There's only one of each in this one, but do be careful. If you have more than one x, all of them become y's. So x equals 2y plus 10. And then we just need to do some algebra to get that y by itself. and whatever's on the other side will be our inverse. So we've swapped our x's and y's. We're now looking at an inverse. Let's get that y by itself so we can talk about the inverse function. So probably do minus 10 on both sides to start. And I wouldn't normally show the minus 10 on both sides, but this is our notes. So I'll go ahead and do it for the sake of our notes. Divide everything by 2. I'm going to write it as 1/2 x minus 5. If you'd rather write it as x over 2 minus 5, or if you just want to have it as one big fraction, x minus 10 all over 2, that works fine. There's a lot of different ways to write this. But there we go. That's our inverse. Our inverse function, f inverse of x, is 1/2 x minus 5. Any questions about that? I have some questions for you. Hey, go ahead and write down what the domain of that is. Okay. Okay. Elliot. Anything that's not in the domain of this, it's a line, it's a linear function. So everything? Everything. And the fact that the domain of the inverse is everything, what's that mean about the range of the original? Same thing. All right, got another question, unless somebody has a question for me. I'm doing this off to the side. What is f of 20? What is f of 20? I'm asking you for f of 20, so you should be looking at your original function. Can you guys find that pretty quickly? Do the math in your head. What are you getting? 50? All right. What is f inverse of 50? If I plug 50 into this, what am I going to get? Half of 50 is 25 minus 5 is 20. You think that's a coincidence? Okay, this is kind of like the machines in the factory, right? We put chickens in one side, chicky nuggies come out the other side. If I have my inverse machine, I should be able to put chicky nuggies in the input and get chickens out the other side. I'm sorry if you're a vegetarian. We put, what are veggie burgers made out of? Delicious grains and vegetables into one side. All right, let's do another one. Oh, this one looks fun. Look, that's a rational function. So this one's going to be a little bit more fun. And it's got x's in a couple different places. I'm getting excited. This will be good. Let's do the same thing we did a second ago. Let's find the domain of the original and use that to predict the range of our inverse. So let's fill out as much of this thing as we can before we even get started. So I'm going to do some side work here for domain of our original function, f of x. This has got a fraction in it, so do what you got to do here. Don't wait for me and copy my answer down. Do what you got to do. You guys have practiced this a bunch. And let's practice writing that in interval notation. I'm just going to go ahead and copy it down into my table over here. My hope is after reviewing with our mid-unit review, you guys are pretty confident coming up with that domain fairly efficiently. If not, that might be a good indication that might be a good idea to come in and see me. Like today, after school, we'll be going over that. Hey, I got some great news for you guys. It's like not immediate gratification news though. After our test 2 weeks from today, I'm going to stop making you write this stuff in interval notation. Okay, we're just doing this for just our first unit. After our test, you'll be able to write this as all real numbers except -5/2. Not that that's like less to write, but some people are going to prefer that. So, but for right now, let's just keep on this interval notation. So when we got to use it later, it's ingrained in our brains. Does that help you fill out anything else in the table here? Yes, indeed, because the domain of the original should match the range of the inverse. So let's go ahead and copy it over here. So we'll have a problem very similar to this on our test. And the way I'll grade this, if you make a mistake on the domain, but you've copied the same wrong answer down for the range, I'm going to give you points for knowing that these two things go together. Does that make sense? All right, now comes the fun part. You guys ready for this? All right, there's a process to this, and I'm going to walk you through it. This process comes up in several different contexts throughout the year. So I want you guys to pay close attention, ask questions. All right, maybe we'll do a little annotation as while we're at it. So we know our process. We're gonna write y equals, it's x minus 3 over 2x plus 5. I normally would not write this down if I were doing this on an assignment. I would probably start with the first real step, which is to flip-flop all your x's and y's. Now remember, all of the x's become y's, not just the top one, not just the bottom one, but all of them. And this is where my students kind of have some trouble sometimes because they're like, how am I going to get y by itself when y is in two different places? And this exact same thing is going to come up again in a couple other contexts in chapter 2 and in chapter 4. So here's the deal. I'm going to walk you through the steps. First of all, we don't want to deal with fractions if we don't have to. So in a complicated situation like this, my first step would be to clear the fractions. Do you guys know what I mean when I say clear fractions? What I mean is multiply by something on both sides of your equation so that your denominator cancels out. Again, I wouldn't normally write this down again, but for the sake of my notes, I'm going to. So my first step would be to multiply on both sides by 2y plus 5. I'm going to annotate my steps off to the side here. So what we did here was swap x and y, and what we did here was clear fractions. That's going to cancel this 2y plus 5, and it's going to leave us with 2y plus 5 times x equals 3 minus y. I'm going to go ahead and distribute down into my next step. So I'll distribute this x. So this is going to become 2xy plus 5x equals y minus 3. All right, what's our goal here? What is it we're trying to accomplish? We want to get y by itself. Keep your goal in mind. We're trying to get y by itself. This is tricky because y is still in two different places. Can't get y by itself if it's in two different places. Somehow we want to try and combine these two things with y's together. Anybody got an idea how we'll do that? All right. So the trick is we're going to end up factoring out a y. We're going to end up getting everything that's got a y on one side of our equation, and then we'll factor a y out, and there will just be one single y left in our equation after we do that. Okay, but the next step is we need to sort the equation out so that all the terms with y's are on one side, and all the terms without y's are on the other side. You guys know what I mean by terms, right? I'm counting 4 of them here. I want these 2 terms on one side, and I want these 2 terms on the other side. It doesn't matter which side you get them on. I'm going to get all my y terms on the left. That's usually what I do. So I'm going to go minus y on both sides. And then I'm going to get rid of this 5x. I'm going to go minus 5x on both sides. And I know I'm not lining up like terms here, but that's okay. So this is a key step, and this is usually where my students kind of forget to do, is at this step. They forget to get all the y terms on one side, and they start trying to divide both sides by y, but then you end up with y's and fractions, and it's just not great. So from here to here, this is a key step. And what we're doing from here to here is we're collecting y terms on one side. And I've run out of room, so I'm going to have to do a little shuffle over to the second column here. Now that everything with the y is on one side, what am I going to do with these 2 terms with the y? We're going to factor them out. It's going to be y times something equals, and it's still going to be negative 3 minus 5x over here. Once we've done that, though, there's only going to be one y left in our equation, and then we'll be able to just divide on both sides to get that y by itself. So factor out a y. That's going to leave you with 2x minus 1. And I didn't leave myself much room, but factor out y. And can you see the last step now? How are we going to get that y by itself? Well, it's multiplying by 2x minus 1. We're just going to divide on both sides by 2x minus 1. And now we're going to have y by itself, so we're done. So I'm going to go ahead and write down my final answer. F inverse of x equals negative 3 minus 5x over 2x minus 1. All right, we got a lot going on in this problem, so I just want to pause here for a second, make sure we're all on the same page, and make sure we can kind of see the forest for the trees here. Okay, so what were we trying to do? We're trying to find the inverse of this function they gave us. Okay, how do we find an inverse? Swap your x's and y's. So that was our first step. That got us to here. And then from there, all of this other work was just to get y by itself. The tricky thing about this is because we ended up with a fraction that had y's in the top and bottom. Okay, when we're trying to solve for a variable, and that a variable appears in the top and bottom of a fraction, typically this is the route we're going to take. So we're going to work to clear the fraction out, get it into a bunch of terms, and then you want to get all the terms with that variable you're trying to solve for. So for us, get all the terms with y's on one side. That will then allow you to factor that y out so there's just a single copy of it, and then you can divide to finish it up. All right. Any questions on that? We're not done. Do you feel comfortable finding the domain of this thing? Let's do that. What's the domain of this thing? Well, we know 2x minus 1 can't be 0. So negative infinity to a half and a half to infinity, basically everything except for a half. And if that's domain for the inverse, then we have also, by default, found the range of our original function. Everything except for a half. I got a couple follow-up questions to ask you guys, but I want to pause here and see if you have any questions for me first. All right. My turn, I guess. Look at this original equation. You guys have graphed stuff like this last year, I think. Probably used your calculator a lot to do them. These things that have x's in the top and the bottom of a fraction, when you graph these, a lot of times these had asymptotes, oftentimes a horizontal and vertical asymptote. Based on the domain and range of this function, I'm focusing just on the original function, not the inverse right now. Based on the domain and range of the original function, can you make a guess where the vertical asymptote is on this thing? I'll tell you there is one. Where are you going to guess the vertical asymptote is for this thing? This is kind of a preview of some stuff we're going to do in chapter 2. Anybody want to make a guess? What do you think? Negative 2 and 1/2? Negative 5 over 2, same thing? Yeah, that is where the vertical asymptote is going to be. That's the only x value that won't go into this thing, right? And when you're going to see that on your graph, where you'll see that gap, that negative 5 over 2, negative 2.5, is you'll have a vertical asymptote there. Anybody want to guess where the horizontal asymptote of this thing is going to be? What do you think? It's going to be y equals 1/2. Yeah. In fact, let's check this really quick. Could you guys get out your graphing calculators? I want to graph this function. Make sure we're comfortable graphing this function. I've had a couple people ask me questions about graphing these rational functions. There's something special about these, especially if you've got one of the older styles of calculators. You do often need to put parentheses around the numerator and denominator when you're putting it into y equals. So parentheses, I'm going to do x minus 3 divided by 2x plus 5. We all have calculators, guys. We need to get those. Can you get them for me today, please? You can check them out. They might not have batteries down there, but at least grab a calculator. And if you're not able to get batteries, check back with them later in the week, and they'll get you some batteries. I'm told that they found the calculators. We had, like, at one point 40 calculators, and they have found those. We don't have our batteries, although they've had some, because some of you guys have checked out calculators, and I'm assuming they gave you batteries. I see a couple yellow ones out there. Did you check that one out this year, or is that from last year? No. That's okay. Same batteries, or have you replaced them? You had to replace them. Yeah, get them today. Let's make sure we got these things so that you guys are comfortable using them before our test. They do have them. Yeah, they have them. It's just unknown whether they've got batteries down there. It takes 4 AAA batteries. If you're not able to get batteries, let them know. Let them know, like, hey, there's no way I'm going to be able to spend that kind of money on batteries right now. Let them know, and they'll work on getting you some. Okay. We've got the office is getting involved in helping us out with that at this point. But let's get them going. All right. Go ahead and hit graph. I'm going to actually hit zoom 6 just to make sure I'm in my standard zoom window. And we predicted there'd be a vertical asymptote at about negative 2.5. Do you see it? Can you see it on your graph there? I'm seeing that vertical asymptote here. That's where the graph is swinging upwards and downwards. It looks like it's, yeah, between negative 2 and negative 3. And can you kind of see this one's harder to see, but can you kind of see how the horizontal asymptote might be somewhere, it's close to 0. Might be, we predicted it was going to be at 1/2. That seems reasonable that it could be to me. If we wanted to change our window, we could get a closer zoomed in look at that, but I'm feeling pretty good about that. All right, one quick last thing for you guys, okay? And I don't want you to miss this because this is important, because at some point you're going to be working on a problem like this on your assignment for today. And you're going to look in the back of the book and you're going to have done everything right, and you're going to see a different answer in the back of the book, okay? And I don't want you freaking out because there are multiple ways to write this thing, okay? So first of all, this is a fraction. Do you know what happens if you factor a -1 out of both the top and bottom of a fraction? Does that change anything if you factor a -1 out of the top and the bottom? Wouldn't that -1 just cancel with itself? Yes? Okay, so keep that in mind. If you looked in the back of the book and you saw a different answer, what I would encourage you to do is go ahead and factor a -1 out of the top and bottom of yours. If I factor a negative out of the top, it would just be 3 plus 5x, agreed? And the bottom would turn into what? The 2x would become negative and the 1 would become positive. So I would probably write that as 1 minus 2x. These two things are exactly the same. They are both the exact same function. Okay? So with a rational function, you can factor a -1 out of the top and the bottom and still get the same thing. Or another way to look at this is, what if I multiplied this thing by a fancy 1? -1 over -1. I would get this, right? Multiplying by 1 doesn't change anything. It just changes the way it looks. Question? Why didn't I not put the 2x there, -2x first and a +1 at the end? Oh, why didn't I put the 5x first? That's a good question. Yeah. I agree with you. I would kind of rather see it first too. But it is the same, right? Same thing. I could have put the -2x here and the +1 at the end. Right? So there's lots of different ways to write this. You're getting the idea, right? There's lots of different ways that I can write this, and they're all correct. So don't freak out if you look in the back of the textbook, which I hope you're in the habit of doing now, and you see a different answer than what you got. Just take their answer or take your answer, multiply it by -1 over -1, and see if it looks the same after you do that. Will you guys give that a shot for me? All right, ready to move on? Questions first? Yep. Pass is available. Any other questions? All right, let's do one more of these. We're not going to worry so much about domain and range for this one. We're just going to go ahead and find the inverse. So go through those steps that I just showed you. Think of this as y equals the square root of x plus 5. Let's go through, flip-flop your x's and y's, get y by itself. Let's see what we get for our inverse. So I'm not going to show as many steps here. This would be more like what I would do if I were doing this in an assignment. How are we going to get that y by itself? Well, we're going to need to get rid of that square root. I think we'll probably end up squaring both sides. All right, are we in agreement? The inverse is x squared minus 5? Okay, I got bad news for you. That's wrong. It's missing something, okay? And I'm gonna show you two different ways why it's wrong and how we can fix it. It's an easy fix, okay? Don't freak out, it's gonna be fine. I'm gonna show you 2 different ways, okay? The first way I'm gonna show you is algebraic, and this may not make 100% sense to you, and then I'm gonna go back and I'm gonna show you graphically why it doesn't work, okay? So stick with me on algebraic. what is the range of my original function? What kind of numbers can I get out of this thing? Could you come up with an input that would spit me out a 0 for this? I think you could. What would you put in for x to get a 0 out of it? Negative 5 plus 5 is 0, and then you would end up getting a 0. Can you think of an input that would give me a negative number for my output? Is it possible to get a negative number out of a square root? No, square roots will never give you a negative number. They can give you a 0, and they can give you all the positive numbers that you want, but they're never going to give you a negative number. So, would you agree with me that the range of this function is x values greater than or equal to 0? I'm sorry, y values greater than or equal to 0. I need to erase that. Y value is greater than or equal to 0. And does the graph kind of confirm that as well? The range is y value is greater than or equal to 0. So here's the thing. If that's the range of my original, shouldn't that be the domain of my new function? Shouldn't it? Well, that's a problem, though, because x squared minus 5 is everything. The domain here is everything. Okay, so what we have to do in this case is we need to fix our final answer. Our final answer is going to be, yes, the inverse is x squared minus 5 as long as, now our restriction up here is that y was greater than or equal to 0. What's that going to change into when we find our inverse? X is greater than or equal to 0. This is our inverse function. It's x squared minus 5, but only if x is greater than or equal to 0. This little bit at the end says that's limiting what I'm allowed to stick into this. So if I came up to you and I said, could you please put negative 10 into this function for me? You'd say, no, you can't. Negative 10 doesn't work in this function. Okay? Let me show you how this works, why this is wrong, and how we could fix this graphically. You guys still with me? If I graph this function, this is a parabola. Which way does it open? Opens upward. Where's my y-intercept? Negative 5. Would you agree that my parabola, my inverse function, would look something like that? Yes? Does the original function and the inverse function look like they are symmetrical with one another? No, they're not. However, I feel like I could chop off half of my inverse and make them look like they're symmetrical with one another. Do you see the half I'm thinking about? What if I just kept this half of it and then I chopped off that half over there? Now it looks symmetrical, doesn't it? All right, so I'm going to say my inverse is this parabola, but I'm only keeping the half of it where the x values are greater than 0. Then it matches my original function. All right, so this is one of those little minor detail things. I will put one of these on the test. What I need you to know is that anytime you're dealing with a square root function, that this can come up. And there are some other functions where this could happen, but we won't see them until later on. So what I need you to do, if you run into a function where I ask you to find the inverse and it's a square root function, at the end I need you to pause and ask yourself, is this actually the inverse function? And either look at the graph and say, how much of this do I need to chop off to make it match? Or look at the original and say, okay, what's the range of the original? It's always going to have a restriction in terms of y, and then when we're doing the inverse, we know we switch y's into x's, just add that on at the end. Okay, I don't want to spend a ton of time on this because this is super minor. Okay, you forget to do this on our test, you're looking at like maybe 1 point out of the 87 points the test is worth. Okay. Any burning questions on that before we move on? All right. We're not going to finish our notes today, but that's okay. I do want to do one of these last examples, and then we'll do the super messy one later on. Okay. The last type of problem you're going to see, they're going to ask you to verify that two functions are inverses of one another. Okay, so the type of problem you're going to see is they're going to say, this is f of x, this is g of x. Can you verify that they are inverses of one another? And the algebraic way that you do this is you don't go through and you find the inverse of this and match it up to this. You actually have to use composite functions. You need to do f of g of x and g of f of x, and we should get x for both of them, okay? I want you to think about my my machine. What are we making on our machine this time? We put in ice cream, we get a banana split. Let's just do that. Is that okay? Sorry if you're lactose intolerant. All right, we put in ice cream, you get a banana split out. Inputs ice cream, outputs banana split. If I make an inverse machine to this, how does it work? Put a banana split in and you get out ice cream. Now let's say I take my original machine and I hook it up to my inverse machine. Okay, so they're the output to input. So I put the ice cream in, it spits out a banana split, but that immediately goes into my inverse, and what comes out the other end? Ice cream. Ice cream went in, ice cream came out. You're good. Okay, thank you. Ice cream went in, ice cream came out. X went in, X went out, right? Now if we reverse it, let's say I do my inverse first. I'm going to be putting in a banana split. In the middle, I'll get some ice cream, but then when it goes through the original function, another banana split comes out, right? So if they're inverses and you stick them together, whatever you put in one end should come out the other end. Does that make sense? In the middle, it's going to turn into something, but that second machine is going to just do the exact opposite and turn it back into its original thing. So algebraically, we say that if I have two functions feeding into each other and I input x, and I get x out, that's good. But then I would also want to hook them up the other direction and feed them into each other the other way and make sure that when I put in input, I get that same input out. So in order for us to do this, we're going to have to do this twice. A lot of times that's not a big deal like this first one. You guys are going to see on Wednesday when this does become a big deal, but you'll have to stay tuned. So let's do the first one. In order to do this problem, I need to do two pieces. I'm going to need to do f of g of x. You all know how to do f of g of x. We've practiced it. It's just substitution. So g of x is the cube root of x minus 2. So find me f of that. How do you find f of that? Well, take your f function and substitute this in for x. I actually really enjoy these problems because like they kind of look messy at first, but then at a certain point you start seeing how it's going to come out to be x. Can you see it already? Can you see how that cube root's going to cancel with this cube? And this is going to become x minus 2. And then we've got that plus 2 at the end, and that plus 2 and that minus 2 are going to cancel out, and we're just going to get x. Woohoo! We're halfway done. So we just hooked the two machines up, our inverse and our regular function. We put an x in, we got an x out. That's good. That means that one machine is doing something and the other machine is undoing it. Now we need to flip the order and make sure it works the other way too. So this time around we're going to do g of f of x. And I expect that it is going to come out to be x. And folks, I'll tell you, on the assignment problems they're going to give you, and on the test problem I'm going to give you like this, they will be inverses. I'm not looking to see that your answer is x. I'm looking to see that all of your steps in between are sound. That you guys are actually showing all the pieces in between. We're verifying. This is almost like a proof in geometry. We know what the answer is supposed to be. We need to show systematically that we get that answer that we're looking for. So for this one, I would urge you to try to do this one without copying my screen. Try and do it on your own. You guys have done lots of f's of g's of x's and g's of f's of x's. I find these problems really satisfying because there's a certain point where you're like, oh yeah, I see how this is going to turn out. Oh yeah. 2 steps and we'll have x. All right. Any questions on that? We're not going to do this last one today. We'll start with this on Wednesday, and I bet you guys are really excited about this. If you're not, look at it closely and realize that when you do f of g of x, you're going to actually need to be taking this whole fraction and putting it in for x here and here in this thing. You're going to have a fraction that has two really messy fractions inside of it. And then we're going to simplify it, and it's really cool because it will turn out to be x. It's just going to take a lot of simplifying to get there. And on Wednesday, I'll also introduce you one of my favorite concepts of all time, which is fancy ones. And you've seen them before, but I like calling them fancy ones. A lot of what we're going to accomplish in this class, we will accomplish by multiplying by fancy ones. All right, that's what I got for you for today. There is one problem on your assignment.